Alright, so now we're going to be talking about transforming variables. So the reality is that not all variables observe linear patterns. So it's possible that two variables observe quadratic pattern, cubic pattern, or exponential pattern. So in those cases, the least square line doesn't work because if your data points look like this, it's clearly concave up, then it's very bad to use a line to fit these data points. So the least square line doesn't work. Okay, so the way to fix this is what's use so-called power transformation. So we still do the least square line. But instead of doing it for xi and yi themselves, we raise xi and yi to a power, different power, possibly the same power instead. And sometimes instead of the power of xi, yi, we use natural log. Because natural log is close enough to a power of x. So in this case, we get an equation which is least square, but not a line because it's to a power. So the equation looks like y to the a equals to beta 0 hat plus beta 1 hat times x to the b. Left hand side could be ln of y, and right hand side here it could be ln of x instead. So let me give you a few examples. So it's if a is equal to 1, b is equal to 2, then we get y is equal to beta 0 hat plus beta 1 hat x squared. This gives you a quadratic model. And if a is ln of and b is equal to 1, then we get ln of y equals to beta 0 hat plus beta 1 hat times x, which gives you y is equal to e to the beta 0 hat times e to the beta 1 hat x, which is equal to a times e to the kt. This gives you an exponential model. And if a is ln of y and b is ln of x, then we get ln of y equals to beta 0 hat plus beta 1 hat ln of x, which gives you y equals to e to the beta 0 hat times x to the beta 1 hat equals to k times x to the r. So this gives you a power model which assumes that y is proportional to power of x. And the power is unknown. So now the question is, how do we know which one to use? So there are two ways. The first way is just make guesses and look at the residual plots. So make several guesses and look at the residual plots and see which one's better. And the second way is what's called use science. So sciences have told us many models that we have already figured out. For example, populations. Population growth is proven to be exponential model. So we don't have to guess on that because we know scientifically population grows exponentially. And same with many other things. All right, so let's do an example here. Let me move this over. So let's do an example here. Okay, so let me divide it into two parts. Okay, so we have data points x and y. So this first plot is the plot with x and y. And the second plot, this is the residual plot. This is yi hat versus residual ei. So it doesn't look like the line fits well, and if you look at the residual plot, there's a trend. looks like this. So there's a trend, because it looks like EI is negative for YI hat in the middle, and then EI hat is positive for YI hat large. So there's a pattern here. This tells you this is not a good residual plot, which means this is not a good model. And we say this is biased. So we shouldn't use this model. So instead, we do. So we try 1 over x and y. So 1 over x is, remember, this is technically x to the negative 1. So this is a power transformation. That in that case, this new plot is the plot with 1 over x and y. And this on the right is the residual plot, which is yi hat versus ei. All these are calculated using Excel. Then if you look at this residual plot, this is better because this doesn't really, compared to the one on the left, this is better. It's nice. There's no trend, and doesn't look like the variance changes as yi hat changes. So this is homostatic. Yep. So this is good, which means this model is better. And well, I'm missing this. So this is our value of beta 1 hat, and this is our value of beta 0 hat. So the model we're gonna get is y is equal to beta 0 hat, so it's 4.932 plus beta 1 hat, which is 0.274 times, notice it's not x, it's 1 over x. So this is a better model for the data points. It's not a linear model, but it fits pretty well. Okay, so let's do another example. To the right. Okay. So here we have x and y, and suppose we are given scientifically that y is equal to k times x to the r, then this tells us that ln of y equals to ln of k plus r ln of x. So it makes sense to do linear regression with ln of x and ln of y. So first we calculate ln of x and ln of y. So this is the plot with respect to ln of x and ln of y. And there's a least square line here drawing the dots. So this is the least square line. And after we find the least square line, we calculate the, so this is ln of yi hat, the whole thing hat, and this is ei, the residual. And this is our residual plot. So it doesn't look like there's any trend. I mean, it looks kind of weird, but there's no trend still. And how far the dots are from the horizontal axis doesn't seem to change much. So this is homostatic. So this is a good plot, which means this model is good. So the equation of the line, if you, let me put it down here. So the values of beta 1 hat and beta 0 hat are here. So this gives you ln of y equals to beta 0 hat, which is negative 7.54488, plus beta 1 hat minus 0.225 times x ln of x. So this tells you that y is equal to e to the negative 7.54488 times x to the negative 0.225. And if you press the calculator, you can figure out what the number is. Second, 7.54488, and raise it to the power of e. So we get y is equal to 0.0005288 times x to the negative 0.225. All right.